Hey everyone, and welcome to today's explainer. I am super excited to be your guide today as we dive into Chapter 8 and untangle the whole concept of time and motion. From ancient shadows to the math of modern physics, we've got a lot of ground to cover. So let's just get right into it. Okay, so just imagine a world completely without time. I mean, literally no clocks, no phones. How would you know when to meet up with your friends? Early humans actually had to deal with this. Sure, they could watch the sunset to know a day had passed or track the moon phases for a month, but that left a huge gap. They had absolutely no idea what time it was during the day. They desperately needed a way to chop time up into smaller, measurable chunks.
And that brings us to our roadmap for this explainer. First, ancient devices of time. Then, the pendulum clock revolution. Number 3, calculating speed using dust. 4, uniform versus non-uniform motion. And finally, your final physics challenge. All right, section 1, ancient devices of time, from shadows to sinking bowls. Let's see how our ancestors tackled this. Once people realized they needed to measure time within a single day, they came up with some seriously brilliant stuff. The Arthashastra actually mentions sundials way back in the 2nd and 3rd century BCE, basically tracking shadows as the sun moved. Then came the Gadika yantra, or sinking bowl water clock, in the 5th century CE. In the Middle Ages, we saw hourglasses tracking falling sand, and even candle clocks where melting wax hit specific marks. Though, a strong gust of wind could totally ruin your schedule for the day with that one. But wait, if you want to talk about scale, the Samrat Yantra in Jaipur is absolutely wild. Built about 300 years ago, it is the world's largest stone sundial. It stands a massive 27 meters tall. Because it's so incredibly huge, its shadow moves exactly 1 millimeter per second, which means it can calculate time with an astonishing 2-second accuracy. Literally a giant stone building measuring seconds, it's a UNESCO World Heritage Site for a very good reason. Now, sundials are cool and all, but they're basically useless at night or if it's super cloudy. Early water clocks tried to fix this by letting water drip out of a bucket. But as the water emptied, the water pressure dropped and the flow slowed down. Super inaccurate. So they invented the Gatika Yantra. Picture a small ball with a tiny hole in the bottom floating in a bigger tub of water. It slowly filled up and took exactly 24 minutes to sink. This 24-minute chunk of time was called a Gatika, or Gati, and guess what? Exactly 60 Gatis made up one full day. This was a real game changer. First written about by the legendary mathematician Aryabhata, these sinking bowls were everywhere. Royal palaces, Buddhist monasteries, you name it. And every single time that little bowl sank, someone would literally strike a massive gong or drum. It was basically a giant, incredibly loud alarm clock for the entire town. Moving on to Section 2, the Pendulum Clock Revolution. Enter Christian Huygens. You see, as civilization advanced and people started traveling long distances for trade, a giant water bowl just wasn't going to cut it anymore. We needed precision. By the 17th century, timekeeping got a massive upgrade. In 1656, Christian Huygens invented the pendulum clock. But the backstory here is amazing. He was heavily inspired by Galileo. The legend goes that Galileo was just sitting in a church, staring at a lamp swinging from the ceiling. He didn't have a watch, obviously, so he used his own pulse to time the swings. And he realized, no way, every single swing took the exact same amount of time. Let's break down the physics of that for a second. A simple pendulum is just a bob, which is a small metal ball hanging on a string. When it's hanging dead still, that's its mean position. Pull it to one side, say extreme position A. Let it go, and it swings all the way across to extreme position B, and then right back to A. That whole round trip is one full oscillation. And because it repeats this movement over a fixed interval of time, we call it periodic motion. But here is the absolute most crucial thing to remember. The time period of an oscillation depends completely on the length of the pendulum, not the mass of the bob. Galileo tested this endlessly and proved it. A heavy iron ball and a light wooden ball on the exact same length of string will swing at the exact same rate. This one physical truth is exactly what made mechanical pendulum clocks possible. All right, on to Section 3, calculating speed using dust, the math of motion. Because once we could finally measure time accurately, we could finally figure out exactly how fast things were actually moving. So if you've ever gotten tangled up trying to calculate speed, distance, or time, I've got a cheat code for you from our sources. Just memorize the word dust, D-U-S-T. D stands for distance, U is the equal sign, S is speed, and T is time.
So d equals s times t. Distance equals speed multiplied by time. If you need to find speed, just rearrange it. Speed equals distance divided by time. Stick the word dust in your brain and you're golden. But hold up. There's a catch. The dust formula only works if your units are on the same team. The standard SI unit for distance is the meter. For time, it's the second. So naturally, speed is meters per second. For bigger stuff, we use kilometers, hours, and kilometers per hour. You have to make sure they match. You absolutely cannot mix kilometers with seconds without doing a conversion first, or your math is going to be totally wrong. Let's look at a quick, real-world example. Say Swati rides her bike to school. The school is 3.6 kilometers away, and the ride takes her 15 minutes. What's her speed in standard SI units, meaning meters per second? Well, first, we convert 3.6 kilometers to meters by multiplying by 1,000, which is 3,600 meters. Then we take 15 minutes and multiply by 60 to get 900 seconds. Speed is distance divided by time. So 3,600 divided by 900 gives us exactly 4. Swati is cruising at 4 meters per second.
Section 4. Uniform v. non-uniform motion. How are you moving? Now we've got the math down, let's talk about what motion actually looks like out in the wild. First up, we need to define linear motion. This is super simple. It's just when an object moves in a straight line, continuing in that exact same direction without turning at all. If you hold an eraser in front of you and drop it, it falls straight down to the floor. Boom, linear motion. But it actually comes in two different flavors. On one hand, you have uniform linear motion. This is constant speed in a straight line. Think of a car just cruising perfectly steadily at 60 kilometers per hour down an empty highway. It never speeds up or slows down. On the other hand, you have non-uniform linear motion. This is when the speed keeps changing. If you're accelerating away from a stop sign, your speed is increasing. Or if you throw a baseball straight up into the air, it starts out super fast, slows down as gravity pulls it, stops for a microsecond at the very top, and then falls back down. The speed is always changing, so it's non-uniform. And that brings us to Section 5, your final physics challenge. Test your knowledge. We've tracked shadows, swung some pendulums, learned the dust trick, and looked at linear motion. Let's see what you've got. Here is your challenge. A train is traveling at a speed of 90 kilometers per hour. How much time will it take to cover a distance of 360 kilometers? Grab that DUST formula. You've got the speed, you've got the distance, you just need the time. And check your units. Work it out in your head or jot it down real quick. Got it? Drop your answer in the comments right now. We have come such a long way from sinking bowls of water, haven't we? But before we go, think about this. If time is just a human invention to measure motion, what happens when we travel so incredibly fast that time itself begins to bend and slow down? Keep observing the motion around you, stay curious, and I'll see you in the next explainer.